So we're continuing on with Kirchhoff's laws here, and we're going to get into a little bit more complicated questions. So our purposes are pretty straightforward. We're just going to solve some problems. That's it. So I've got a few examples to go through that compound on top of what we just did. So just as a summary, in our series, these are the equations. In our parallel, these are the equations. And we can use V equals IR in our equations as well. We just need to be specific what we're dealing with. So V1 equals I1 R1. And we cannot mix up those subscripts. So I can't say voltage across resistor 2 equals current 1 times R3. They have to be the same subscript. So we're going to continue to use this with some examples. So here's our example here. What's the potential difference supplied by the power source? So that's just what's the total voltage. Notice here why we're more complicated. We have a parallel in a series. This section here, this is our parallel part. You're going to have to get comfortable with recognizing this parallel. So inside this red box, we can only use our parallel equations. Everything outside is going to be series. Now, one strategy we can use with solving these is to take that part, the parallel part, and combine them into a single resistor. Because this new diagram here looks a lot nicer. I've got two resistors in series. That one's much easier than dealing with this parallel. So this one I can simplify by combining those together. So what I need to do first is figure out what RP is. Now this equation here for the parallel, I've tried something different. Instead of doing 1 over RP equals 1 over R1 plus 1 over R2, I've just used this reciprocal sign. You can try it out, see if this actually is nicer for you, or if you like doing the fractions. Both of them will get you the exact same thing. It's actually the same equation, just written differently. Plug in numbers, we get RP is 8. So once we've got that, we can actually look at this series circuit. So our total is R1 plus RP. Pretty straightforward. That's just 16 ohms. We have I total, it's 2. So I have I total, I have R total, solve for V total. The V total is just 32 volts. So there you go, that's the potential difference. Again, one strategy with this, combine parallel resistors into one. That's one strategy. There's going to be a few others shown up here. Here's another example. So we again have a parallel portion within a series portion, just a few more resistors. We want to solve for what is V1, what is V2, what is R2. So V1 is just the voltage across R1, V2 is the voltage across resistor 2. In this case, I am not going to combine my two resistors together that are in the parallel part, so R3 and R4. The reason I'm not going to is I4 is within this parallel part. So that is not the current running through the parallel, it's just through R4. Remember, our current law states that my total current splits into the current across the third resistor and the current across the fourth. So I4 plus I3 must add up to the total, but I don't have that yet. So I'm going to go through and solve and try and get I3. First thing I'm going to do, notice I have I4 and R4. Automatically, again, if you have two of the three voltage currents resistor across one resistor or the total, get the other. Even if you don't need it, that's just going to be part of the steps to figure out what you can work with. So V4, just those two things times each other, we get V4 is 6 volts. Now how that helps us is, since R3 and R4 are in parallel, remember the parallel equation, both of these two voltages have to be the same. That's the rule with parallel. And then we can get I3 because I have voltage 3 and R3. So now I have I3, I have I4, I can get my total current because those two add up to the total. Notice I'm already 4 steps in and we're not at the final yet. So this is why you solve for one thing, it helps you get the next, which helps you get the next, and so on. How does I total help us? Well, there's a couple things I can get with this. Let's get V1 first, because my total current is equal to current 1, which is equal to current 2, because those are all in series. So with my current 1 and my resistance 1, I can get voltage 1. That's going to be the first easy step. There's one of the things. Now, to get V2, what I can do is look at my total voltage. So my current, it gains total voltage. It must lose V1, lose V2, and then lose either V3 or 4. It doesn't go through both of those resistors. It just goes through one. So I can use this total voltage equation to be able to solve for V2. There's that. Now the last thing to do is get resistance 2. I have I2, V2, can solve for R2, no problem. So notice my strategy with this, and if you're confused as I went along, that is okay. Get comfortable with being uncomfortable, because you're going to work your way through these questions. Again, like I said, you're not going to know if you're on the right track. You're just going to solve one thing, which helps you solve another thing, which helps you solve another thing, and you see how that works in this question. All right, another example here. We want what is the total power dissipated by the 3 resistors in this circuit. So I want P total, power total. So just like V equals IR, this Ohm's law works for all things. It's the same with power. So I can deal with power 1, power 2, power total, use all those equations. So in this case, notice I wasn't given what this R value is. I labeled it R3. You can label things as you like, because sometimes they don't give you everything. So I'm going to show you another strategy. So the last one I tried going forwards, I'm going to show you backwards. So I want total power. Well, one way I could get that is V total times I total. That is one of the equations. I have V total. That's great. I don't have I total. Well, how could I get I total? Looking at this diagram, I could get I1. The problem is I don't have V1. I have R1, but I don't have V1. Well, how could I get V1? I have the total voltage, and I know the total voltage is going to equal V1 plus V2, so I could use this equation. The only thing I need for this is voltage 2. Well, how could I get voltage 2? Use the equation that's there. So notice I worked my way backwards and said, okay, to get power total, I need these 2 things. What am I missing? How do I get that? Okay, is there anything missing there? Yes. I don't know what V1 is. Well, how could I get that? Use this. Do I have everything? No, I don't have V2. How could I get that? So this is another strategy you could do, is work your way backwards. So if you're struggling to go forwards, try going backwards. Because once I get V2, it's like a domino effect. I solve this, I can solve this, get to the end. So let's go ahead. So power 2, we can get for voltage 2 like this. Pretty straightforward. Plug that into the other equation, we get what V1 is. Take V1 and plug it into the I1 equation. Solve for I total, and with I total, get power total. There you go. So that's another strategy you can try. If nothing else is working, work your way backwards. That is the end of Kirchhoff's laws. That is probably the hardest section in the whole year, in the whole course. So if you can do this, you can do everything else, you're good to go. If you're struggling with it, that's okay. There are many students who have struggled with this before. Remember, just try something. If you're struggling to move forwards, try backwards. Write some equations down. Just try. If you're just sitting there the whole time just staring at it, nothing's going to happen. You got to actually try something. So here we go, way back to the very first Avengers movie. Take a look. See what does not work with this one. So as cool as this scene is, this does not seem possible at all. First of all, we can talk about size of the rotors. If you take a look at a helicopter, how big the helicopter rotors are compared to the body. The rotors here are quite a bit smaller compared to how big the actual ship is. So the likelihood is these 4 propellers are not going to be big enough for them to be able to lift up the entire helicarrier based on how massive it is. You'll notice here it's weird, the wind is blowing into them, which shouldn't make sense. It should be blowing down and through those blades. That doesn't make sense. And the fact that these propellers were spinning in the water, electronics and water do not mix, or they mix really well. So that's one problem. But then also doing those propellers in the water is actually going to be quite difficult. So that's what's wrong with this one.